Okay, here's theorem 33, and the basic idea is to prove that if this composite function takes you directly from A to C, so you have two functions, they're both bijective, that's what this bij here means. So f maps A to B bijectively, in other words 1 to 1, and g maps B to C bijectively, 1 to 1. Okay. Then the inverse of the composite function fg, or if you're reading it from left to right, gf, it exists. Now, there is an inverse, and it's of this form, right? So f inverse g inverse, and interestingly, this and this are bijective. Now, I'm wondering which I could present first. I think I'll... So, let's assume we prove that this is the inverse of this. Okay? Now, I'll go back to theorem 30. Remember, with that if and only if proof, both ways, that if you had a bijective function, then you had its inverse. And if you had its inverse, that function was bijective. That was theorem 30. So here's a function. If we can prove that's its inverse, then that's bijective. Okay, by theorem 30. We spent quite a bit of time on before. Now, conversely, this here is the inverse of that. You assume we can prove that, right? But that's the inverse of that. And therefore, by theorem 30 again, if this is the inverse of that, then this is bijective by theorem 30. Okay? So both of these are bijective. Now I could go one step further and show closure, but I'll keep the punchline for a bit later. But you're probably becoming increasingly suspicious, right? You know, obviously you're smelling a group coming up because we've been talking about the identity function, which is sort of equivalent to the unit element in a group. Associativity. We're now talking about, we're about to prove that this is the inverse of this. We're talking about inverse. And next I'll talk about closure. And then we've got the four properties of group. So I ask you to, at the back of your head, try to imagine just what this group, talking about composite functions, what is this group? What is this group going to be? I'll pose that as a challenge. See if you can dream it up ahead of me, right? Ahead of me telling you what it is towards the end of the lecture. All right, so we now have to prove that this is the inverse of that. Right? All right. Well, by analogy, let's go back to groups and elements. Now, let's say little g belongs to big G. So big G here's a group. Okay. So now the unit element belongs to the group. It's the definition of group, must have a unit. Now for every element G in the group, there's an inverse. So G inverse of G equals G of G inverse equals E, right? That's the definition of an inverse element. So if we're going to find, now these are elements of a group, but up here we're talking about this and this, and these are functions. Okay, so we need to, with our functions, we need to use this and this sort of like that. I mean, this is kind of an analogy, right? If we're going to prove that this is the inverse of that, we need to get something like that. So what we have to prove is that this applied to that cancels, that this cancels out that. So try to prove something like this. F inverse G inverse times this, so G inverse, and you end up with just the do nothing. Now, does that sound plausible to you? You're trying to show that this cancels out this, so that what you're left with is the identity function, right? So that, I mean, this is a function you use to change nothing. So if this is the inverse of that, if it is, then applying this to that will give you the identity function, right? I mean, the right-hand side means do nothing, so nothing has changed. Now, if you apply this, of course things change, right? You've mapped. Well, you've gone from that F takes you there and G takes you there, so F and G, and then G inverse will take you back, and F inverse will take you back further, right? So, so this, in a sense, cancels out that. So takes you back to where you started with. Okay, so arbitrary element A. All right. Well, let's try to prove that this does equal to that, right? All right. So let's do this. I hope you can see this. All right. So F inverse. Now, from the definitions of composite functions and associativity of functions, now we can rewrite this in the following form: G inverse I think this is right. 23. Just check the text. So far so good. All right. So now here we have three functions, okay, and we can assume associativity. We proved that before, so we can rewrite this in the following way. We can instead of putting the brackets around these two, we can put them around the two G's. So okay, that's just from associativity of three functions. Now, what's this? Now look, G is bijective, right? Therefore, this function G has an inverse, a unique inverse. So there is a G inverse, and here it is. Now, what do you get? So this will be F inverse. Now, look, what is this? In term, I mean, physically, what's going on here? So here's your B, here's your C. Now, G takes you from B to C, right? And G inverse takes you back from C to B. Okay, so that's the same thing as doing nothing in B, set B. So this, do G first, right? And then G inverse. So what that means is you start in B, so little element, any random element B of big B, your domain. You do G, and then you do G inverse. So you just end up where you started with. So this is just identity of B. Now it's B. Can you see that? Because if I apply this function, this identity function for set B, big B, on any little element B of it, I'll just get B, right? And this cancels this, and little g does what? Well, it operates, it maps little b. Okay? So for this we get this, the identity function times f. All right, now we can rewrite that. Now I of b operating on f. Now go. That was what? That was theorem 29, was it? A lot of the 7 theorems in this lecture. Yeah, that was theorem 29. So theorem 29 said that IF is just f, right? So we can rewrite this as f of the inverse f, right? It's just f. Okay. Now, what does this mean? Now, this similar logic to here is here, but this time it's from A to B. Now, f will, here's your little a, just a random element of set big A. Okay. So do this first. It's on the right hand side. So f will take you from big A to big B, and then f inverse will take you the other way. It takes you back to A. So they can, this cancels out that. It's the inverse of this. So that is the same as I. What? Which I is it? What letter do I put down here? Okay. Well, doing f and then f inverse is the same as you did nothing with these a's. So this will be little big A. Okay.